C. You know what? I'm going to save these before I start. Save as PDF, yeah. Okay. Section 2C, combinations. Combos. Okay, combinations are very, very, very similar to permutation, except a few differences. So we'll mostly just talk about what is different about a combination. Well, the formula, we'll sometimes write it NCR. Sometimes we write it C with N comma R as like a function. Sometimes we write it that way. Some textbooks, we won't really do this because it'll get confusing later. Some textbooks even write it this way, or some websites, if you're looking at other websites, you might see this notation. We're not going to use that because we're going to learn about matrices later. And so that will start to be really confusing. So I'm going to take that away. However, I just wanted to mention that, if you're looking at websites or something, you might find that kind of notation. So what is the formula for a combination? It's almost the exact same formula as a permutation, except for one difference, and that's that we divide by this r factorial. So again, just for comparison, n permutation r was n factorial over n minus r factorial. Combination is the same thing, except we're also dividing by this r factorial. So what is the difference between, that's the formula, okay, but why use combinations? What's the difference between a combination and a permutation? Why do we have different formulas for them? What's going on? So with permutations, order matters. Okay. So that's the big issue with permutation, or with permutation, order matters. So you're talking about codes, you're talking about roles, you're talking about places, as in first place, second place, third place, etc. That's the kind of permutations we're talking about. Now, with combination, order does not matter. That's the difference. If order doesn't matter, then there's a lot less ways that you can rearrange things. For instance, there's 4 of us on this Zoom call right now. How many different ways can you make a group of 4 with 4 people? There's only one way. There's only one way to make a group of 4 people with 4 people. However, if we rank them as in alphabetical order, well, then there would be form permutation for factorial. So there's different ideas there. So if you're just making groups, order doesn't matter. So combinations really has to do with groups. Making groups of things is really going to make the difference between whether or not you're thinking of a combination or a permutation. Now, of course, all through section 2C homework, you're thinking about combinations, and all through 2B, you're thinking about permutations. But once you get to the idea of on the exam and you get, you're just thinking about, you're just faced with some word problem, then you have to make that decision. Is this a combination or is this a permutation? So in that kind of situation, you have to really start thinking about what is it you need to use. But first, let's just do some evaluation. Let's try 10 choose 3. That's going to be 10 factorial over 10 minus 3. Oh, I was a little early on that factorial. Factorial over 3 factorial. Okay, So that's going to be 10 factorial over 7 factorial, 3 factorial. So this is going to be 10 times 9 times 8. We've done a lot where we go down to 7 factorial and then we cancel that out. So hopefully it's okay. I skipped that part. And then 3, 2, 1. Okay, so let's evaluate it. We have 3, 3. So the 9 becomes a 3. 2 with the 8. 8 becomes a 4. So we have 3 times 4 is 12. And 12 times 10 is 120. So there's 120 ways to group 10, let's say 10 elements in groups of 3. Okay, let's make sure. I'm seeing I have 10 things. How many groups of 3 can I make? There's 120 ways to do that. That's what we just said. Okay, so combination has to do with groups. There's 10 elements, 10 items, 10 things. You're making groups of 3. I claim there's 120 ways to do that. Okay, so that's what we're talking about. Let's try something like 25, choose 23. Again, I'm just using that other notation. It doesn't mean anything significant. This is going to be 25 factorial over 25 minus 23 factorial over 23 factorial. Keep forgetting that parenthesis. So 25 minus 23 is just 2 factorial over 23 factorial, 25 factorial. So what do we get? We get 25 times 24 over 2 times 1. And it looks like we can go cancel the 2 with the 24 to make 12. So then we have 12 times 25. And I think that's 300. So I claim there is 300 ways to group 25, we'll say items this time, in groups of 23. Okay, that's how we can understand what we just figured out. Okay, so hopefully that kind of makes sense. Let's look at a very particular set. Example, let's have the set A, B, C, D, E, F, G. And let's find groups of 3. Okay, let's find groups of 3. How many groups of 3 out of these elements? 1, 2, 3, 4, 5, 6, 7. 7 elements. Okay, so the number in the set is 7. Okay, so how many groups out of 7, or how many groups of 3 can we make out of 7 items? That's going to be 7 choose 3. So that's 7 factorial over 7 minus 3 factorial over, again, 3 factorial. 7 minus 3 is 4. So we have 4 factorial, 3 factorial. And so we have 7, 6, 5, 4 factorial. We can cancel that out. 7 times 6 times 5 over 3 factorial is 3, 2, 1. That's 6. We can cancel a 6. So 35. Okay, 35 different ways. That's our 35 different ways to make groups of 3 with 7 elements. Okay, not too exciting. What about groups of 6? How many ways can you do that? 7 factorial, 7 minus 6 factorial, 6 factorial. And that's going to be, well, 7 minus 6 is just 1, 6 factorial. 7 times 6 factorial cancels. You just get 7, okay? Now I want to show you a little bit of symmetry that goes on with these combinations. Let's just do all of them for 5. So 5 choose 1. 5 choose 1 is 5 factorial over 4 factorial, 1 factorial. And that's just going to be 5. Okay. 5 choose 2, 5 factorial. 5 minus 2 is 3. 2 factorial. So that's 5 times 4 over 2 equals 10. 5 choose 3 is 5 factorial. 5 minus 3 is 2 factorial, 3 factorial. And we just did that. That's 10. So that's what I'm talking about. There's symmetry with these. 5 choose 4. How many ways can we do that? 5 factorial. 5 minus 4 is 1 over 4 factorial. So we get 5. Okay, that's the same as this 5. 5 choose 5 is 5 factorial over 0 factorial, 5 factorial. 0 factorial is defined to be 1, as we did before. So this is just 1. And this is linking up with 5 choose nothing. How many ways can you have 5 items and you choose none of them? It's just 1. So you can see that there's a bit of symmetry here going, where you have 1, 1, 10, 10, 5. Oh, I forgot this 5 here. Let's do 5. Make that into a 5. There you go. So you can kind of see there's symmetry. 1, 5, 10, 10, 5, 1. So is there anything we can learn from this? Well, something like 7 choose 6, I know is just going to equal 7. Just like before, we had, if it's 1, if you're choosing 1 before the total, it's just that number. So you can kind of go from there. So what am I saying? 101 choose 100 is 101. We can just learn that. Another way you can learn is 7 choose 1 is also 7. Anything choose 1 is just that number. So that's something, I mean, with practice, with your homework, you'll see these types of things. And anything choose 0 is just 1. Okay. So that is also going to be true. So you can look out for that. So say 1 million choose 0 is just 1. Anything choose 0 is just 1. How many ways can you not choose anything? There's only one way. And then also n choose n, any number is also just 1. So 100 choose 100 is just 1. Okay, so there's some symmetry, and that should kind of help with, or, kind of look out for that when you're calculating these things. You can kind of see the symmetries. Hopefully that will help. Let's do more examples. Let's do some examples of story problems. Let's say we have 4 finalists chosen from 13 applicants. How many ways can that happen? If you have 4 finalists, let's say there's some kind of job opportunity, 13 applicants, we're going to choose 4. I claim is 13 choose 4, but hopefully it makes sense why this wouldn't be 13 permutation 4, because in the previous section, it was all about the permutation. That's all we were doing. And, so hopefully it makes sense why it would be combination and not permutation. I claim this is a permutation problem. 13 factorial, 13 minus 4 factorial, 4 factorial. 13 minus 4 is 9, 4 factorial. So we have 13, 12, 11, 10, 9 factorial. I can cancel the 9 factorial. 13, 12, 11, 10, 4, 3, 2, 1. Let's see. Well, 4 times 3 make 12, so I can just cancel it in that way. That's pretty nice. And then this 2 I can reduce with the 10, and that makes 5. So now I have 13 times 11 times 5. That's going to be 13 times 55. And what is that? I should know that. 715. So hopefully it makes sense why that'd be a combination. We're not putting these people in order. We're not putting them, we don't have particular roles to put them in. So I don't have, say, I'm not doing vice president and speaker or anything like that. It's just we're making out of 13 people a group of 4. So that's why that would be a combination and not a permutation. So hopefully that makes sense. Very important when these questions are out of order that you understand when to use what. Okay, let's form a committee, a high school committee. And it's going to be of 2 freshmen, 5 sophomores, and we're going to choose, this is chosen from 5 freshmen and 8 sophomores. Okay, so again, we're making a committee that has 2 freshmen, 5 sophomores, and this is chosen from 5 applicant freshmen and 8 sophomores. So how can we find how many committees are possible? Again, we're not picking roles, we're just picking how many ways this can happen. Well, with the freshmen, we have 5 to choose from, and we're choosing 2. And from sophomores, we have 8 to choose from, and we are choosing 5. This is the same instance. It's the same instance, so I'm multiplying and not adding. It's only one scenario. This is only one scenario, so I multiply instead of add. Remember in our branches where we kind of multiplied across. So that's how I'm thinking. That's why I'm multiplying, not adding, is because this is all the same instance. Well, let's calculate and see what happens. So 5 choose 2 is going to be 5 factorial. 5 minus 2 is 3 factorial. And then 2 factorial. 8 factorial. 8 minus 5 is 2 factorial. 5 factorial. So we're getting close. If you want, you could even just, because these are being multiplied, you could even cancel the 5 factorials in this way, but I worry that we might have problems, so I don't usually do that. So let's see, 5 times 4 over 2 times 1, and then 8 times 6, 8 times 7 times 6 over 2 times 1. There we go. And let's see, what can we get rid of? 2. So the 4 becomes a 2. And then with this 2, we can either turn the 8 into a 4 or the 6 into a 3. It's totally your option, totally your choice. I guess I would pick that to be 4. So we have 5 times 2 times 4 times 7 times 6 as our answer. Let's see what that is. 5 times 2 is 10. 10 times 4 is 40. 40 times 7 is 280. 280 times 6 is 1,680. We see that same number again. It's kind of interesting. So that's how I believe you would do a problem like that if you were forming a committee in this way. A lot of finite problems do this. So any questions about why is this not a permutation question? I can fully understand if that was confusing of how do I know that that must be a combination? Is anyone confused? Does anyone want to ask me questions about that? Okay, I will take the silence as a no. All right, let's do another committee. So a committee of 7 students, which is composed of at least 5 freshmen from, let's go back. I can explain this better. 5 freshmen, at least 5 freshmen, and we're going to choose is chosen from 5 freshmen and 8 sophomores. How many committees are possible? So we're having a committee of 7. So there's 7 people. We're doing at least 5 freshmen, and then we're choosing it from 5 freshmen and 8 sophomores. So let's figure out what we can do. I have to choose at least 5 freshmen. So at least 5 freshmen means 5 and up. But with this problem, we only have 5. Okay. Now the other one is going to be, let me see. The other one is, we have 7 and we have 8 sophomores. So this should be good. Just double checking something. Seven students with at least. Okay, I thought something was weird because this problem is too easy. So I had to check my notes. It's at least, I'm going to change the problem. At least 5 sophomores is chosen from 5 freshmen and 8 sophomores. If we did it the other way, there was only going to be one scenario, because if we did at least 5 freshmen from 5 freshmen, it has a community of 7, we wouldn't have these multiple scenarios, so there's no point of doing another example. So sorry about that. This should be 5 sophomores from a group of 5 freshmen, 8 sophomores. Again, this is a committee of 7. So let's see. If we have at least 5 sophomores that we are, no, 5 freshmen, we'd have to choose 2 because we're adding to 7, and then 8, choose 5. So the 5 and 2 is adding to this 7 there. Hopefully that makes sense. The other option we could have, since it's at least, it has to be 5 sophomores and up, you could just have, this is freshman, 5 choose 1 times 8 choose 6. Okay, these are the sophomores. There's no restriction that says that we have to have any freshmen at all. It just says that we have to have at least 5 sophomores. So we could do this scenario as well. And we could even do 5 choose 0 times 8 choose 7. There's no restriction there. It says we have to have at least 5 sophomores, so we can do it that way. So let me delete that, make some room. Now we have to actually calculate this. Have we calculated 5 choose 2 before? Yeah, we sure did. In fact, I think we did this exact problem. So that's 1680. So I'm going to copy that because we already did it. Now, 5 choose 1 is just 5. We talked about that earlier. If you have anything choose 1, it's just that number there. 8 choose 6. Okay, so I got to figure out what that is. 8 factorial. 8 minus 6 is 2 over 6 factorial. So this is 5 times 8 times 7 over 2. Turn that into a 4. Now you have 5 times 4 is 20, and 20 times 7 is 140. So we have 140 ways that can happen. 5 choose 0. Anything choose 0 is just 1. And then 8 choose 7. Notice this is a difference of 1. So that's going to be 8 choose 7 is just going to be 8. So there's just 8 ways that that can happen. Now we just need to add them up. We just need to add them up to find out how many ways. So 1,680, 140, and 8. And we should be good to go. I claim that that's going to be 1,708. Okay. So there you go. Sorry about that confusion because I messed this up, but this is at least 5 sophomores. So hopefully we understood the difference. And that's important. We'll see that in the homework where you have to, if you have at least, at most, those are kind of important to catch. So hopefully that's making sense of what is going on. What is the difference? Now there's one other thing I want to mention about combinations that I couldn't mention earlier. We talked about subsets. I think from the very first class, we talked about subsets. And with subsets, so let's say you have the set A, B, C, okay? This one's easy enough where I can fully explain it. So the subsets would be A, B, C, A, B, A, C, and then B, C. That's another option. A, B, C, A, B, A, C, B, C, and then of course you have the whole set. 1, 2, 3, 4, 5, 6, 7. Did I forget anything? Oh, you know who we can't forget? The empty set. So I think that's all of them. Now we have 3 different elements. So the number of subsets is 2 to the n. Maybe I'll write this out again. Number of subsets equals 2 to the n. N is the elements. We have 3, so 2 to the third is just 8. So I claim that there's 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's including the empty set. We already learned this. Why am I bringing it up again? Well, I kind of glossed over where this formula comes from, 2 to the n. But you can show that 2 to the n is the same thing as n choose 0 plus n choose 1 plus ... n choose n. Okay, that's where the formula comes from. So this is also 3 choose 0, 3 choose 1, 3 choose 2. That's a 2. 3 choose 3. Okay. That's 1. That's 3. That's 3. And that's 1. Yeah. 6, 7, 8. Yeah. Okay. So that's how it's kind of linking up to the very beginning. We talk about subsets first, and then we introduce combinations later. But it turns out that, when you're talking about groups, that's where it's coming from, and that's where that formula is coming. So hopefully that makes sense, but that's where it comes from. So that's kind of interlinking from the very first time we got together. So I want to bring that up. All right. I'm going to save these notes.